So let's look at the problem on putting bounds on the zeros of a polynomial. So a polynomial is, I'm going to write it in this particular fashion. So fc is Cn plus a1 Cn minus 1 etc. an. Similarly, g of z, I'll look at two polynomials, Zn plus b1 Zn minus 1 etc. Last term bn. So of course you draw the unit circle, which is always what we or you draw a circle, and what we mean by the zeros are what you plot the zeros and you want to find a bound. So in this case, all the zeros, all the zi's, the way I have drawn, are less than r. So this is the bound we are looking for. So these are very classic problems. There are lots of results on this. I'm going to review a couple of results. So first of all, let me define mu to be the maximum of this so notice that the mu's are not the maximum of the absolute value of the coefficients, but absolute value raised to the power whatever is the index on k. So if this is 2, this is 1 over 2, etc. And similarly, let me define nu to be maximum on all the k's, but for the bk polynomial, the second polynomial. And then let alphas be the, so f of alpha i's are the zeros, and similarly g of beta j's are the zeros of the g polynomial. So f of alpha I is 0, g of beta, just a notation wise, beta is 0. So this means alpha I and here beta I, beta j's are zeros of fc and gc. So we of course want to bound the alphas, and so the first classic result is all the alphas are bounded by 2 mu. And of course, similarly, the betas are bounded by 2 mu also, 2 nu. So if you look at the alpha i's and beta i's, they are bounded by 2 times the maximum of lambda comma nu. So let me prove this quickly. This is easy to prove. So so fc is once again is zn plus a1 zn minus 1 etc. an. So we can write fc over zn is 1 plus a1 over z plus a2 over z squared plus etc. n over z. So now let me take the absolute value here. So it's the absolute value here, but this absolute value is greater than summation ak over zk. This follows from a plus b is greater than a minus b. Okay, using that symbol identity. But on the other hand, you notice that all the AKs are from here. All the AKs are less than absolute value of AKs are less than mu to the power k. So if I substitute it here, so of course minus AK is greater than minus mu k. So this will go 1 minus summation k equal to 1 through n mu over z to the power k. Now let me consider this for c greater than 2 mu. What happens? So if c is greater than 2 mu, for c greater than 2 mu, notice that mu over z is less than half. So consequently, right. So we are going to consider z greater than 2 mu. So mu over z is less than half, or which is the same as minus mu over z to the power k is greater than minus 2 to the power k. So if I substitute that there, this becomes fc over zn is greater than 1 minus half plus 1 over 2 squared plus etc. 1 over 2 to the power n. So this is 1 minus half multiplied by 1 plus 2 plus etc. 2 to the power n minus 1. So that's 1 minus half to the power n minus 1 over 1 minus half. 1 minus half is half. Half cancels. And 1 cancels. So you get the result to be, so this is, because you pull out a half outside, you have 1 over 2, etc., 1 over 2 to the power n minus 1. So this sum of this would be, so that's half outside, then the rest sums up as 1 over half to the power n over 1 minus half, because whatever is the highest power plus 1. So this half and this half cancels. 1 cancels. So the answer is 1 over 2 to the power n, which of course is greater than 0. So the whole point you see is that fc over zn will be greater than 0 if c is greater than 2 mu. That means of course fc itself is, so we get fc is absolute value because zn is not 0. Is greater than 0 if z is greater than 2 mu. So we have proved what we wanted to prove. All the roots are, so there are n roots, so all the roots have to be inside 2 mu. So if this is true for f, it is true for g, and so this inequality is trivial. All right, so let me go and state the Lagrange's result, and then I'll prove it. So Lagrange's result is, of course, a little tighter than this. So what this says is all the alpha is are less than 2 mu, where alpha is are the roots of, where mu is of course the maximum of ak to the absolute value of ak to the power 1 over k. So we are something like this. So this is your 2 mu. So all the roots of fc has to be somewhere in this circle. right. So instead of remember this is your mu. Instead of defining the twice the maximum, Lagrange is able to relax it a little bit. So his LF is the maximum of ak to the power 1k, and you take the next one, the second largest. You need to order these quantities. This is the largest one. This is the second largest one. So I'm going to call this because I need this explicitly. I'm going to define this. Call the largest one to be mu1. So mu1 is maximum over k, ak to the power 1 over k. So let's say this is for k equal to k naught. This is actually for k equal to k naught. Then mu2 is maximum over k, but k is not k naught. Once again, ak to the power 1 over k. So if I define this, I don't need to write all this. So LF is mu1 plus mu2. So you can clearly see that this is less than 2 mu1, and which is 2 mu, right? So the earlier result was all the zeros are within 2 mu. Now the Lagrange's result is that all the zeros are within LF. So I'm going to prove this. So the LF circle is going to be somewhere here. So this radius is now, so this is 2 mu, so this is 2 mu, and this is LF. So it's a slightly better result or tighter result due to Lagrange. Then all alphas are within LF. So once again, we look at Fc over Zn. So we went through this. This is 1 minus absolute value of all of them. So this is, remember, this is Cn plus, so this is 1 absolute value of 1 plus A1 over Z plus etc. An over Zn. So this is going to be greater than 1 minus summation ak over zk, k equal to 1 through n. And so I'm going to obviously look at for z greater than LF what happens. So notice that here among from this definition, k minus 1 terms satisfy in this inequality. K minus absolute value of ak is less than mu1 for k minus 1 of them. We don't know which one, but that's true. So I can rewrite this as and certainly mu is z is greater than mu f, so the LF is of course mu1 plus mu2. So 1 over z is less than, so we have 1 over z is less than 1 over mu1 plus mu2, and AKs are less than mu1 for k minus 1 of them. For such AKs, so if you put this, you see that AK over ZK would be, AKs are less than, remember AK to the power k, so this is less than mu1 to the power k. So this is z to the power k, so this whole thing is mu1 to the power k. So this is absolute value of AK over ZK. So this inequality is true here for k minus 1 such, with the mu1 it is true for all of them. And if you put mu2, this is true for k minus 1 of them. So this inequality is true for all. And if you replace here with mu2, this is true for n minus 1 such terms. Here. So which n minus 1 we do not know, but it really doesn't matter, right? So proceeding, and for the remaining one term, wherever it is, you have this inequality, ak naught over ck is going to be less than what we had before, mu1 over mu1 plus mu2 to the power k naught. Notice that, of course, if I put a minus sign, all this inequality will get reversed. So if I put a minus sign, all these inequalities will get reversed. Now I am ready to substitute this here. So you get fc over z so if k is not equal to k2, you have ak over zk is greater than this quantity. So that's going to be mu2 over mu1 plus mu2 to the power k. And that remaining one term, k naught, it's going to be mu1 over mu1 plus mu2 to the power k naught. And so the easiest thing is, let me define this to be P and this to be Q, to write it. So we can add and subtract this one term here. So this is now going to look like 1 minus summation k equal to 1 through q to the power k minus p to the power k naught. And q to the power plus q to the power k naught, because I also included, so which I'm going to write it as like this. So this, of course, I can sum it as 1 minus 1 over q to the power. Notice that k equal to 1 through n, so I'm going to pull out q. Then this is summation k equal to q to the power k. K goes from 0 through n minus 1. So that's going to be 1 minus q to the power n, 1 minus q to the power n over 1 minus q. But 1 minus q is p, so this is this, minus pk naught minus qk naught. So if I expand this up, if I include this p here, this reads now p minus q minus pk naught minus qk naught from here, then minus minus plus. So this is q to the power n plus 1 over p. In any case, this is positive. So if we can show that this quantity is greater than this, then we are done, because then this is going to be positive. And that is true because of, if you go back and see what we defined p, notice that this is p, so p is greater than q because mu1 is greater than mu2. We had mu1 greater than mu2. So p is greater than q. So if p is greater than q, notice that this is, if you take this identity That's the same as Pn minus Qn multiplied by P plus Q. So if you expand this quickly, you get Pn plus 1 minus Qn plus 1, right? Minus PQn minus QPn. So that's going to be, so this is PQn, and this is plus. So this is going to be Pn plus 1 minus Qn plus 1 minus plus Q. So if I pull out a PQ outside, so this is Pn minus 1 minus Qn minus 1. So from here itself you can, so first of all you can do this by, quickly by induction. So if this is true, certainly it is true at P minus Q is positive. So at stage 2, this is positive, this is positive. So this quantity will be certainly greater than this, and you can see with induction that Pn minus Qn is greater than Pn plus 1 minus Qn plus, so this is greater than Pn plus 1 minus Qn plus 1. So that means this quantity is greater than this. This is positive, so the whole thing is positive. So the bottom line is, coming back to the Lagrange's result, that this is a tighter bound, which is this one. So now let me quickly show you a bound due to Cauchy, and so in some cases the Lagrange's bound is tighter. In some specific problems, Cauchy's bound is tighter. So again, same problem. Alpha is, the first bound is alpha is less than 2 mu, where 2 multiplied by the maximum of ak to the power 1 over k. So this 1 over, so that's the classic bound. Then the Lagrange's bound was LF, which was mu1 plus mu2. So this is actually mu1 according to our definition. Mu2 is the second largest power among the ak to the power 1 plus k. So you had, this is your 2 mu1, and this is the Lagrange LF, and here are the zeros alpha i's. Now notice an interesting thing is, if the polynomial has, if all the coefficients are bounded by 1, so you can trivially see if all the ak's are bounded 1, this is 1, the maximum is 1, all of them are 1. So you trivially get that all the roots are within a circle of radius 2, not 1, 2. So then if you multiply these two polynomials as a Schur product, in other words, define a new polynomial whose coefficient is 1 multiplied by 1. This coefficient is a1, b1, a2, b2, an, bn. So it's still degree n polynomial. That's a nonlinear, or it's a Schur polynomial generated from G and F. Its zeros are also bounded by 2 because of this theorem. Now the Cauchy's result goes slightly differently. So So define M to be the maximum of the absolute values of AK. Notice that in the Lagrange case, you had AK to the power 1 over K, K running from the higher order coefficients to the lower order coefficients. Whereas here, M is the, then all the roots are, so this is Cauchy's result. All the roots are within a circle of radius 1 plus M, where M is, so this is equally easy to prove. So if absolute value of Fz is, of course, absolute value of Zn plus A1 Zn minus 1, etc. An, which is greater than 1 minus, using the same argument, A1, let's say we can write this as sigma A n minus k zk, k from 1 through n, right? But all the M is a greater than or equal to absolute value of AK. So minus M is less, so or the other way. All the AKs are less than or equal to M. So minus AKs are greater than or equal to minus M. So when I take the absolute value, of course here also absolute value. So this absolute value in fact goes inside, which is like this. But absolute value of minus absolute value of AK is greater than minus M. So you can write this as greater than equal to 1 minus M multiplied by sigma Z to the power K, K from 1 through N, by just rearranging these terms. So this will be minus K. But on the other hand, this is a partial summation is smaller than the summation going from 1 through infinity. With the minus sign, we can write this as 1 minus M. K goes from 1 through infinity, Z to the power minus K. But this sums up as absolute value of Z over 1 minus Z. So when you substitute this, this becomes 1 minus mz. I'm sorry, this is Z inverse. This is Z inverse. So this is 1 over m divided by Z minus 1. So when you take this common denominator, this becomes Z minus 1. Then this becomes Z minus 1 plus m. So here you can see the result. This is of course positive if absolute value of Z is greater than 1 plus m. And that's the end of the Cauchy result. There is a little more to it, but I'm going to stop here. So so this all the zeros of all the zeros of the polynomial fc are also bounded by this. So as I said, depending on the coefficients, that bound could be this new circle could be inside or it could be outside, depending. So now it's going to be problem specific.